reactions, it will stop the reaction at that point as well. For this loading criteria. Okay?
But
Do you want to look at it? Will that help? Will that help you?
I'm just overthinking it then. Like, so how are you going to prove?
how do you know you're right?
You would.
Okay.
The only way to do it is by just saying.
So if you solve it the other way, you should come up with the other number.
If we solve it the other way,
You should come
we
up with
better
a 500
get
number.
that R2 equals 542.9 pounds.
And I think that's what you were asking, right?
So we're just assuming that it's going to, right?
Yep.
Okay. I thought we were like.
Do we want to solve it?
No,
we can.
I was
It won't
just,
take
I'm
us
just
long.
curious if that's what you wanted us to do, is to make sure, like, because we didn't really solve for, the sum of moments that equals 0. We're just assuming that equals 0.
Yep.
Okay.
Yep.
See, I thought we had to go through the whole process.
I wouldn't expect that you have to solve the moments on both sides of the bridge. No.
All right. Yeah, because that's where I was confused, because we found one and we're assuming for the other, so we
Yep.
weren't really proving the sum of the moments equals 0. That's
Sure.
where I was getting confused.
Sure.
I'm like,
Do you want to look at it to
No,
see that it works?
I get it. I
Okay.
didn't know we were making that assumption.
Yep.
I thought we were going through it.
Where would you factor in the weight of the beam?
Where would we factor in?
So if you look at C.
So that's a very good question, and that's where it kind of gets into when you have uniformly distributed loads. That's where you would actually. So how is that going to impact us? It's going to impact us in the vertical dimension, right? Our beam is going to have some weight, but that's also going to provide some rotation as well. So it's going to impact you in both the moment equation and in the vertical direction. Okay. The weight of the beam won't affect you in the horizontal though. Okay. So.
If it was 10,000 across the whole bridge,
You split
at
it
5, you would put that 10,000 on the
Yep.
So if it's only partial, say it's only for 5 out of a 10 length.
Can we go over?
What is what?
So really
Kn
where
is
those
kilonewtons.
forces are coming
So
down,
that's the metric equivalent
more
of a
forces
force.
just in the middle.
Okay.
What, can we go over one, like, question D on page 28? What's
Yeah.
That one just looks like it's taking into account of the,
unevenly distributed weights?
Second.
but it's still taking into account, like, it's just pounds, like the road itself.
Okay, well, and that's a very good question. So John is saying, if you look on page 28, part D, he's saying that looks like it's just taking into account the road itself. It's getting us closer to that real world scenario, right? Yeah, maybe the,
Weight, yeah.
yeah, we might have 6,000 pounds distributed over the entire bridge, right? And then from 8 feet going to the left of reaction 2, we have an additional 2,000 pounds. So we maybe have a commercial vehicle sitting on there, or a personal vehicle actually, okay? Yeah, let's take a look at a problem like that, okay? Is everybody good with all this? Does this need to be up on the board any longer? Can I erase and restart? Okay, so let's look at a scenario where we'll have 3 loading conditions, okay?
Keep it on notifications. I don't subscribe to any of your channels, so.
Well, it doesn't mean notifications go automatically.
So we'll put a 4,000 pound point load.
The second one.
5 feet from reaction 1.
Oh, I'm sorry.
We'll have, let's say, a 10,000 pound load.
Oh, so that's the original one. I checked with mine.
Uniformly distributed
3, 4, 5.
over the bridge. And then we'll say that we have a 6,000 pound load. Uniformly distributed. Start starting 5 feet to the left of R2, terminating at R2. Okay? How does this look?
You never determined your distance.
Yep. So 5 foot, we'll put our £4,000. Horribly drawn bridge, sorry.
You're using 300.
Yeah, I just did it with 150.
150 over the sign. Did you use parentheses?
And then we also have
It's 150 is over the sign. I did sign this thing.
£10,000, okay?
So it's 1, 2, 3, 4, 5, 600 times the sum, 45.
Okay, so we end up with a 10-foot span.
Is this adjustment?
Okay? Okay, so our bridge is 10 feet long. At its mid-span, which, oh yeah, those ended up getting a little bunched up.
You also had 200.
Overall.
So 10 feet, 5 feet, so right in the middle we have a 4,000 pound. We have 10,000 pounds uniformly distributed over the entire span. And then we have 6,000 pounds uniformly distributed from 5 feet, so from midspan to the reaction at point 2. Okay? Everybody on board with that to this point? Okay? So what are our equilibrium conditions?
R1 plus R2 equals 20,000. And Y equals 0.
Yep, so all the forces of our, in the Y direction need to equal 0. Okay, and what did you say we had, John?
R1 plus R2 equals 20,000.
Okay, so John is saying R1 plus R2 equals 20,000. Everybody see where John got that from? In agreement? Yeah, okay. And let's take a step back. Do we need to worry about X forces?
No.
On this one? We don't, right? We don't have anything operating in the X direction, so we're good there, okay? We also need to know that the sum of all our moments equals 0, right?
You need your distances too, though. Oh, I see.
You have
got the tick marks. Okay, yeah, you got the tick marks.
So this is 5 feet. This is 5 feet. Below the scale, that worked out poorly, but
So 6,000 is that?
4,000.
so what do we do? So let's not just jump to the conclusion here. How do we resolve these uniformly distributed loads to do our moment calculation? Goodness.
Take the load in half of the length and put it as a force there. So that 10,000 goes across 10 feet, so you'd add
So
it to
put
the
it at
4,000. It'd be at 5 feet, which the 4,000 already is,
Yeah.
so it'll turn into a 14,000 pound load.
Yep, exactly right. So in resolving our uniformly distributed loads, into point loads, what Rush is saying is this 10,000 pounds is distributed over the entire 10 feet. Okay? So we can say that 5 feet in,
At the alley,
we have 10,000 pounds,
7 feet.
but we also have a 4,000 pound load there already. So we have a total of 14,000 pounds being applied 5 feet from each reaction. Okay? Does everybody follow where that is originating and how we're getting that? Okay? So how do we resolve our 6,000 pound load?
Same one.
Same way,
So
right?
it'd be 2.5.
So here it would be, it's over a distance of 5 feet, so we're gonna resolve it at 2.5 feet, okay?
But you put the whole load there, not, you make it.
Correct.
you-
It'd be
We're taking it
6,000.
from a uniformly distributed load
To a point
to a
load.
point load,
Okay.
to concentrating that load, okay? Alright.
So all 6,000 would be good.
So here we have, oh, that's terrible magnitude. There we go, 6,000 pounds. Okay? And here we're at 2.5 feet, okay? Does everybody follow where that's originating? And we're good with that? Okay? Do you want to look at reaction 1 or do you want to look at reaction 2?
I just do the same.
No one has any deep emotional attachments to either reactions? Okay? So let's look at moment around reaction 2 to keep consistent. We have to remember that in order to prevent any rotation, this has to sum to 0, right? Okay? So what combinations of forces and distances do we have?
R1 times.
R1 times 10.
R1 is being multiplied by 10 feet. Okay? What's next?
Minus
14,000 times 5.
14,000 times 5. What's the magnitude on our 14,000? Is it positive or negative?
negative.
Negative, right? As we're grabbing onto our bridge and we're rotating with that force, with our thumb coming out of the board, we're rotating counterclockwise. Okay? So it's going to create a negative moment. Okay?
Minus 14,000?
It doesn't matter.
Oh yeah, sorry.
Oh, there.
Thank you, John.
That matters.
And then it'll be the same with this one, right?
Negative 6,000.
Negative 6 times 10.5.
Okay, because again, grab onto our point, our thumb's pointing out of the plane, we're rotating just like that force would, rotating counterclockwise so we have a negative moment. Okay?
R1 equals the sum of that divided by 10.
So, yep,
No, it would be R2.
10 times R1 pound-feet is going to equal 70,000 pound-feet. That's 15,000
Yep.
pound-feet. Okay? So R1, what is that? 85?
85.
Divided by 10.
85,000 there. Oh, okay, you already did it.
Oops. 8,500 pounds?
So then when you total 14, what is it, 14 and 6, so 20,000, so
So what does that tell us about R2?
11.5.
So our R2, in order to meet this equilibrium equation,
Yeah, I get that.
R2 equals 11,500 pounds, okay? Let's take a moment and let's look at, just look at our bridge deck. Don't take into account these magnitudes. Given the loading condition, does it make sense that we need a more robust resistance at this point than we do at this point?
Yeah.
Right? Okay, good. Does anyone not see why we need to provide more resistance at this reaction than we do at this reaction? Okay, good. Now, we have more load on this side. More load is going to be concentrated in that element, okay?
I think this stuff is easier than this forced polygon.
I would agree with you. I would agree with you.
Now that we're going through it, yes.
Yeah. Yeah, the force polygon needs a little bit more of an intuitive leap.
Yeah, I'm still
I'm-
lost
yeah.
on B.
I'm
I
not
can't
the
figure
strongest
out
there
the
in force.
Lost on which one?
B,
Okay.
I still can't figure out the right.
We've got time. Do you want to look at it and let's get it set up?
For which one?
So I wants to go back to
Section
on page
1.4.
17.
Yeah, section 1.4 B.
Oh, back to these.
Terry, the other thing that I'll say going forward, the problems are going to be more like the bridge one where we're solving for more moments, less like the force polygons, okay? We're gonna get more into real world applications and work less in the abstract, okay? What's the distance between your reactions?
It's a total distance of 20 feet, and then the 300 pounds is fixed at 8 feet from the right, 12 feet from the left. Yeah, right in there. 300 pounds.
300 pounds?
Yeah.
I've set an alarm for 11:15, so I know
To wrap her up.
we can start wrapping it up. I also talked to Larrabee yesterday, so
Did he really?
What did he have to say?
he's good. He's good. We talked about something called block scheduling with Durand. And it was a good, healthy conversation for everyone involved.
Come at you saying what the Frank?
No, and I'd sent him an email. Okay, what else does it tell us? What's this distance?
6 feet.
Which question is this?
That's why.
BD.
So this is B on page 17.
B.
Okay,
B as in boy.
so if this is 6 feet and this is 8 feet,
It's a 3, 4, 5
it's a
triangle.
3, 4, 5 triangle, right?
But it's not. Because if, based on what Rush gave me for the answer, then our angles aren't 30, 60, 90, they're different. Or no, maybe that's a 30, 60, 90, but it's on the force polygon, never mind. It's a 3, 4, 5, and you get 30, 60, but on the force polygon, what are your angles on your force polygon for B? Like 58 point?
53 and 36,
Yeah,
53 and 36.
plus with some decimals, but so you got
Okay.
54 or 37 and 53.
yeah.
So we have a bad problem, is what you're saying?
Yeah, it's not a
Okay.
3, yeah,
And so, yeah, so we don't have a 90-degree here.
Right,
exactly.
right.
Okay.
It's obtuse, so
Yep,
it doesn't follow your,
sure.
you know what I mean?
Yep. It's not following its own example that it's giving you. Is what you're
Pretty
saying?
much.
It's going outside the box a little bit.
They didn't proofread it. Yep. Okay, so, well, that's okay. Let's, for the sake of this problem, and we're being asked to solve this, correct? We're not
Yep.
being asked to
Yes,
Yep,
solve this.
that's
exactly.
correct.
The other side doesn't matter.
Okay. So,
Sides matter.
let's go ahead and we'll suspend the disbelief of what's actually going on in the picture, and we'll use this force,
Yep,
use the angle that you have here,
yep.
and draw this member to complete your force polygon with the line of action that you need to close the polygon, okay? If we think back to what we talked about with force polygons in general, if we were to draw it with the actual lines of action that it has, and we don't close that polygon, what does that tell us? Do we have static equilibrium?
No.
No,
It has to be closed.
we're gonna be rotating this thing somehow, okay? So in the field, how do we resolve that if we don't have it? It could be. It's whatever we need to do. I think this one is, aren't these two anchor bolts sunk into something?
Yeah, like the ceiling.
Yeah, it's like,
Like a hammer drill in the ceiling.
We call it a road, basically.
Yeah, so, okay, yeah, so we've got, so let's think of it as, the thing that always comes to my mind is a suspended running track in a gym, okay? So if we're looking at this and we've got two cable stay supports, but we aren't gonna get into equilibrium, what do we just need to do? We just need to figure out what angle and at what magnitude do we need to put that in, sink another anchor in there, and then we'll get to that equilibrium, okay? So that's how we would actually deal with this scenario in the real world, okay? So how do we want to draw our polygon? What's the first element you want to draw?
300.
You want to draw our 300 pounds in the vertical?
Yep.
Okay. And then how should I draw this element?
It'll be at 60 degrees from horizontal.
60 degrees from the horizontal? Yep. Okay.
I did.
X.
So then that would be 30 degrees.
Yep.
And then the top one would be 60 degrees.
Okay.
So that's where I'm at, and from what now I just do sine of,
Now you kind of diverge on the options that are available to you. Whether you
Right.
want to look and
sine.
just solve using sine of what it is, or if you want to resolve with the law of sines. Which one do you want to look
I
at?
just do the sine, like the
Okay.
sine of 30,
I'm a little,
right, or it'd be 60?
If you want to use sine, you'd have to use the 60 degree.
The sine of 60 times 300.
Equals x divided by 300, right? So x equals 300 pounds times cosine of 60 degrees, okay? And if we wanted to use law of sines, we would just say 300 pounds is to sine of 90 as x is to
What are we times it by, the cosine of
sine of
60
60.
degrees? For the top one?
Oh, yeah, sorry.
Oh, okay, because you had sine there, so.
Yep. No, I wrote sine initially, and thanks for pointing that out, Marshall. Okay.
so when I did that, first of all, this week. Doesn't work. So, this one is actually, I had it was there, so
13.8
times the
Yeah.
whole negative. Well, because I was doing it the way I did it equilateral, but. So I'm doing it that way.
Are we assuming it's 36?
Yeah.
Yeah, I would just, even though because if you draw, what John asked is, are we assuming that it's a 30, 60, 90 triangle? If we don't assume that it's a 30, 60, 90 triangle, I was just gonna calculate this for you, what this angle is. If you draw this the way that it actually is, you're not at equilibrium.
Right.
And you're gonna yank one of those anchors out, or you're gonna pull out of the reaction point. Let's see.
Then is that a flaw in the book or what?
Yeah, that's a printing error in the book.
Extra.
I feel like I should get extra credit for that.
What is it supposed to say?
What's that?
I'm not seeing the strap.
So the bottom interior.
Oh, we gotta go.
If you have to do it's 57, top right's 37.
I'm gonna upload it.
The left length would have to be way longer than the right length.
Yeah, they just didn't draw it geometrically correct.
The lengths that they put on aren't correct.
Yeah, yep. Yeah, I've set an alarm for myself to go off at 11:15, so.
Larry be up there tapping his foot at it, so.
I talked with him on Tuesday too, so he knows that if you guys come in a little bit late, he's not good. Like, shouldn't be all over you.
No, he gives a
he's-
shit, but you know how he is.
Yeah.
You know.